calculate the current version. Oh, okay. Introduce it. Seek. Better version of C. This is super interesting because Rust is great, but connecting it with C libraries is not so great. Less is more. Blah, 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 blah. C++ a gigantic language. Yes, understand the project files. After you init command from the C compiler, some new files are created inside the current directory. First, a source directory is created containing two files, main.sig and root.sig. Sig module, which is simply a text file. When main function leaves, if you're building an executable program in C, you need to declare the main function represents the entry point of your program. Building a library. Root. I wonder why they call this root and not lib, but whatever. Okay, traditional files in a working directory. Build.sig, build.sig.son. Know what this. The first file represents a build script written in C. This script is executed when you call the build command from the C compiler. Low-level languages normally use a compiler to build your source code into binary executables or binary libraries. Nevertheless, this process of compiling source code, blah, blah, blah. Programming world, once project became bigger as a result, programming build systems with our second set of tools to compile and build and blah blah. CMake, blah blah blah, all of this suck. However, these are separate tools, do not belong to C like GC or CLang. In SIG, we don't need to use a separate set of tools to build our projects. This is good. We can use this build system to write small scripts in SIG, which describe the necessary steps to build compiler SIG project. Nothing more. This is great. It's a JSON-like file which can describe your project and also declare set dependencies of your project that you want to fetch from the internet. External libraries. Ooh, okay. One possible way to include external external C library in your project is to manually build and install the library in your system and just link your source code, blah blah blah. Which describes the project. You can easily include this library, but okay, so you need to have a build.sig.son file in the repository, which means you cannot pull C projects just like that. I guess people are kind of making their own mirror copies of the C repositories. Package.json or the pip file or the cargo.tom. Let's see, you might notice that very few let's install SIG highlighting. Notice the import. Yes. We use these built-in functions to import functionality from other SIG modules into a current module. The import works similar to the include preprocessor, the import statement. In this root.sig file, we can also see how assignments, create a new project, are made in SIG. You can create a new object in SIG by using this syntax: const var name value. This is nice. I like this better than let. In the example below, we're creating two constructs, testing. So the standard library, and I guess this is the test module of the standard library. You can write a test, expect the fn keyword. In this root.sig module, will declare a function called add, which has two arguments named a and b. The function returns an integer, blah, strongly typed, colon character. Okay. Standard debug prints to std error. Std out is for the actual output of your application. Gzip. Writer on the file, std out, writer, push. So this tells you this function. Or an unsigned in or an error. In this example, the return annotation of main indicates return an error. This is the try keyword, executes the expression stdout print. If the expression returns a valid value, then the try keyword does absolutely nothing. It's like if the expression does return an error, then the try keyword will unwrap the error value, then it returns this error from the function and also prints the current stack trace to std error. Because in high-level languages, somewhere in the stop, if you don't want to stop, you really need to face the error. Okay, so far nothing out of this world, but let's try to do save build test. Let's do something. Save build test, run the tests. Save run. Just do a test. What's in here? Standard optimization allows for it, so between debug really safe, really fast, really small. Standard optimize option. Oh, is this like in Swift? where you can pick preferred optimized mode. Ooh, I like this. This is really cool. Release fast. Yeah, nice. Because what does this take? It takes, I guess this is a pointer and the standard optimize options with this struct, and it returns an optimize mode. It's cool. I like it. So I guess here we're passing just an empty struct. This creates a module which represents a collection of source files alongside some compilation options, such as optimization mode, link, and system libraries. Every executable library will compile with BASIC on one or more modules. Or other entry point main.sig target the optimization mode. Aha, okay, so okay, this is kind of cool, right? Like you can define the entire build pipeline within one file instead of having to run several commands like you do with cargo. You can just in this one build.sig file have your entire compilation chain process. Add import function. This is what allows SIG source code to use import foo where foo is not a file path. In this case, we set up x.mod. Okay, so you're kind of setting our root as SIG sample underscore lib, which I guess it means if we wanted to, we could do something like import what's this? SIG sample lib, right? Or something like that. Oh, okay. So I have to do const sample lib, right? And here in my sample lib dot would you look at that? This is really cool. I like it. Like I knew the SIG compiler was powerful. I just kind of surprised by how good this is. It's very customizable. Allows you to define all of the, let's say, aliases that you want, right? In a very programmatic way, which I like. Okay. Blah blah blah. Compiling the entire project. Gross size with perfect build process and to build scripts sort. No. When you execute the SIG build command, the SIG compiler will search for a SIG module called build.sig. Yes, yes, yes. 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 SIG standard library. Oh, I was just about to ask which project use Seek right now. So Bun is the most famous one, everybody knows. Mach game engine, I never heard of this one. What is this? This is cool. 4K is not that much, but Llama 2 Tiger Beetle, I know that it uses Cyclab here. Okay, so it's not that much. You can add Ghosty and leave Ghosty to here, so that's good, but still not super famous software, right? Constant variables. Yeah, how does this work? Right, so let's start with something. Let's start by playing around and why is this down here? Okay, it doesn't matter. So I have my main function and I want to, let's say, and okay, got the used. No, that will work. What if I set this to undefined? Aha, okay. And then I do, what if I have a function that is add one, then I take my A, which is a U8, B, no, just one, and then 3 plus 1. And then I do var H plus 1 and 1 H. Local variable is never mutated. Okay, that, yes, whatever. It doesn't matter, right? But doesn't it warn me against uninitialized autofix? I don't know what this does. Okay, and then H plus 1. I guess I have to do const std. Okay, these are tests for something else. Can I write a test for my main function? I guess not. I mean, it doesn't matter, right? Like, we can do this still the same. Define this. I'm just playing around and trying to see what's going to happen. So if I do save, build, test. What's the error? Yeah, because I don't need my lib module. I don't need this. this. Okay. There's a lot of steps on this build script, which, I mean, it is annoying if you just want to get running as fast as possible, but it is definitely very valuable. And I get no output. This is what is confusing me right now. Why am I not getting any output? Tests. If I have no expectation, well, no. Try. Let's try a test. Always fails. Try STE test. Expect. Okay. Compilation error. Main test always fails. Failed. How does this work? Okay, let's keep reading. Maybe the answer will become clearer. Hello, I am learning SIG. Let's just say it doesn't make me too happy to write advanced Rust. It gets fairly hard just to follow the language at some point. And I just want to see if SIG is any better, especially once you start getting into the more advanced patterns. Maybe it's just a little bit easier to write and to understand. Any way to catch, enforce, function signatures. runtime safety checks that can catch undefined behavior in debug builds. You can enable them. Okay, I can add assertions. It's common undefined pattern. Use a more explicit approach with error handling. Nope. Compile time checks, yes. You can use comp time to enforce values that are not compile time. Nope. No value use cases. This is kind of what I want, but what worries me is that you can just do this and it's not complaining. It's just allowing you to pass an undefined value. Which is just a little bit confusing for a modern language. There's no such a thing as unused objects. Every object being constant variable you declare in SIG must be used in some way. Doesn't matter which way you use it, as long as you use it. If you try to break this rule, if you try to declare an object but not use it, the SIG compiler won't compile your SIG code. Unused constant. Explicitly discard. When you assign a special character in SIG, which is the underscore. When you assign an object an underscore, discard the value in this particular object. You must mutate, yes, primitive data types, U8, 8-bit integers, sign integers, floats, C char, C short, U short, arrays. Okay, so you have slices, array operators, runtime versus compile time, no length. Blocks and scope. Okay, let me just, I need to know I don't trust Copilot that much. say have this. Yeah, okay. Here it catches it. It doesn't catches it in the function. This is confusing. Why would you do this? Is there any way to enforce it here? So I have optional times. Run the test with runtime. Well, this is also wrong, right? I declared it as const, and then I'm trying to add to, but I don't get a compiler error, at least not there. It's complaining about the undefined value and not that this is a var. Okay, no. Same as the function is just taking it. I am confused. But okay, I guess. I mean, it would be really nice if the compiler would help you to point out whenever there is a undefined. But I guess not. Guess one just needs to be really careful. Okay. Scopes. Strings in C work very similar to strings in C, but they come with some extra caveats, which adds more safety and efficiency to them. You can also say that SIG simply uses a more modern approach, modern safe approach to manage and use strings. Array of arbitrary bytes, U8 values similar to string C, which also can be blah blah blah. Now, because a string in C is an array, you automatically get a length of the string embedded in the value itself. This makes all of the difference because now the C compiler can use buffer overflow. To achieve the same kind of safety in C, you have to do a lot of work that seems kind of pointless. Much harder to do in C. It's 25 string literal, get the length. Okay. Blah 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 blah. Iterating through the string. If you want to see the actual byte, you can use a for loop. Each byte is a hexagonal decimal value to the terminal. Print statements. Okay, so bytes represent the object. For oh, this is interesting syntax. This looks like a lambda. Much better. Oof, my eyes. Okay. To check the type of any object, you can use type of function. You can find this array for elements, 32 bits. Okay, so I have a simple array, I have a string object. I do type of the simple array, yes. I do the type of a string literal. The reference, I guess, yeah, this is a const reference, which means you can modify it. And of the yeah, constant pointer of 16 elements or 16 bytes. That's why we get 16. Okay, it's null terminated. Means the 0 means null terminated. It is a slice object. Okay, so that's why you don't get the memory of it, because you don't know. Byte versus Unicode points. Okay, there's a lot here that I'm not going to go into right now. But this is nice. std mem equal split scalar split sequence given a substring delimiter. Okay, start with ends with trim count. Okay, very useful stuff. It's kind of weird that they're in the mem, but I guess if the strings are just an array of bytes, then it's just treating them as bytes. Equal. That are being compared to. This is a lot of work to compare to strings, but again, if they are trying to replace or improve on C, then it makes a lot of sense, right? Like, you're not going for a high level abstraction, you're just going for raw bytes. Start with blah blah blah. Safety engine. Okay, safety in SIG. In general trend, modern low-level programming languages is safety. As our modern world becomes more interconnected with technology and computers, the data produced by all of this technology becomes one of the most important and also one of the most dangerous assets that we have. Blah blah blah. Failment, true safety in technology. In other words, we have won't be exploited 100% certainty. Safe language, operating system. Rust. Rust is for the most part a memory safe language by enforcing specific rules to the developer. In other words, a key feature of Rust, the borrow checker forces you to follow specific logic when you're writing your Rust code, and the Rust compiler will always complain every time you try to get out of this pattern. In contrast, the SIG language is not a memory safe language by default. That undefined kind of proves the point. There are some memory safety features that you get for free in SIG, especially in arrays and pointer object. There are other tools offered by the language that are not used by default. In other words, the SIG compiler does not obligate you to use such tools. The tools listed below are related to memory safety, that is, they help you to achieve defer. Allows you to keep free operations physically close to the locations. What is this? This helps you to avoid memory leaks, use after free, and also double free problems. Furthermore, it also keeps free operation logically tiled at the end of the current scope, which greatly reduces the middle overhead. Error defer helps you to guarantee that your program frees the allocated memory even if a runtime error occurs. Pointers and objects are non-nullable by default. This helps you to avoid memory problems that might arise from dereferencing pointers. Yeah, but integer, it is nullable, right? Like, okay, whatever. SIG offers some native types of allocators, call it testing allocators that can detect memory leaks, double freeze. These types of allocators are well used in unit tests, so they transform your unit test into a weapon that you can use to detect. Complex. Arrays and slices in SIG have their lengths embedded in the object itself, which makes the SIG compiler very effective on detecting index out of range type of errors. But what if you get like a JSON message from like the internet? How would the compiler help you there? Despite these features that SIG offers that are related to memory safety issues, the language has some rules to help you achieve another type of safety, which is more related to program logic safety. These rules are: pointers and objects are non-nullable by default, which eliminates an edge case that might break the logic of your program. Switch statements, okay, good. This is nice. Switch statements most exhaust all possible options. The SIG compiler forces you to handle every possible error in your program. Okay, this is very nice. Okay, syntax, also some pretty technical. Just a quick recap: functions, objects, strings, arrays, slices. Blah, blah, blah. Object-oriented programming can be done in SIG through struct declarations. We are not going to do object-oriented programming because object-oriented programming sucks on the long run. Basic control flow syntax, enums, pointers and optionals, error handling with try-catch, unit tests, yada 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 yada. Okay. Continue, break, if else. So try, print. This is funny that the print takes more options. It gets verbose at some point. Switch statements. I like switches. Kind of looks like a pattern matching kind of switch, which is very nice, right? Like you have your enum, and then each case, you can just use with the dot operator, which looks like Swift, which is really cool. I like that. And yeah, I guess here you're just declaring your string slice, you're assigning it to it. Then the compiler takes care of adjusting. Right, look, this is going to be a slice of the creation of the created string, so you don't need to know the length. It's good, I guess. But I don't know, I would prefer that the compiler shouts at me if the compiler shouts at me if I'm forgetting to initialize a variable. Switch statements must exhaust all possibilities. Yes, this is good. They do have an else, which I guess is the default. That's very nice. 1, 2, 3, professional beginner category. You can also do this as a variable. Looks very nice. I mean, it has definitely taken a lot of the lessons learned over the last few years, right? Like, reminds me a lot like to Swift, but Swift is again one level higher, just like how you handle strings. Here you can tell it's like very low memory, or very, very low, like low level. It is a slice of bytes. But then you have this very nice things like being able to use the enums, with this dot operator. This is very, very nice. Then you can also have like your switch with specific values, right? Like if you're just using an integer, you can use them in your switch. Using ranges, that's also nice. Yeah, so very powerful, the switch. Okay, the defer keyword. Now we read about this, and I wasn't understanding it. Zig has a defer keyword, which plays a very important role in control flow and also in releasing resources. In summary, the defer keyword allows you to register an expression to be executed when you exit the current scope. At this point, you might attempt to compare the Zig defer keyword into the sibling in the Go language, also has a defer keyword. However, the Go defer keyword, Go, behaves slightly different than the sibling in Zig. More specifically, the defer keyword in Go always moves an expression to be executed at the exit of the current function. If you think deeply about this statement, you will notice that the exit of the current function is something slightly different than the exit of the current scope. Okay, so let's just read the example. STD, you get your STD out. You have your full function, and it's just called from main. So defer exiting function. Okay, so it just puts it at the end of the scope. How long have you been programming for? Wait, let me think. I am now 35. I started around college. I started quite late. I used to play a lot of video games, but I didn't code. So I started pretty much when I was 18, more or less. 19 actually. So it's already, what is that? 14 years? 15 years? Yeah. That's when I started. Okay, therefore we can use defer to declare an expression that's going to be executed when your code exits the current scope. End of current scope. What do you consider the end of the current scope? The current closing so with the last expression in the function, like, yeah. That will be my next question, is like, how does it deal with async programming, coding? How do you deal with threads in Zig? That's because in Rust it's a lot of pain to do async programming and multi-threaded programming in Rust. Like async by default is like kind of multi-threaded, so you have to use a lot of send and sync, and it gets complex. Like the function signatures get complex really fast. You have to deal with lifetimes and passing around values, and it's just you waste a lot of time. Like it does give you the guarantee that your program will work when it runs in a ASIC environment, but it's just painful programming async in Rust. Before we continue, it's worth emphasizing that the defer keyword is a conditional defer, which means that the given expression will be executed no matter how the code exits the current scope. Huh. So you might try to free memory, or print something, but if it's not initialized, you might crash. The error defer, the conditional defer is only when you exit the current scope on a very specific circumstance. When an error occurs in the current scope. Okay, they're LIFO for loops. Actually, let me try one thing. I still haven't tried to run this, so I don't know what to do. See if run. See how do I run this? Split one positional argument. And what was it? Zero debug? No. Oh, debug. I thought this was supposed to be cached. Again, this is like this. You need to rely on your tests to catch initialized, released. What was it? Fast release. Release fast. Yeah, you see, and here it's like 0. I don't like this, but I don't know. Okay, so for Pedro, I can try this. Let's just do that. So you get the index that way. Ah, okay, so you have, okay. So the first one is going to iterate over the bytes on the string, and then the second one is going to create an index next to it. And then here instead I can do char, right, and it needs to be discarded. Okay, like while, yes, like your typical while. But then I like this. While can be confusing, right? Like you can forget about setting this, and sometimes I always set it. The moment I write the while, I set it just below, even when I do it in JavaScript or Rust or whatever, because otherwise I just get into whatever I was doing and I forget about it. So if the language supports like this syntax of like the step immediately afterwards, this is nice. Using break, continue is nice as well. This is like really a nicer version of C, really it is, right? Like I can see that it's not going to solve the same type of problems, let's say, that Rust attempted to solve. It's just a much nicer way to write C code. Kind of halfway reading this. Struct and OPP. OOP. This is a language more closely related to C than it is to C++ or Java. Because of that, you don't have advanced OOP. Yes, you don't need this anyways. You need like objects, yes, because you need to encapsulate behavior, but advanced like inheritance and yada yada, you don't need that. You really don't need that. Interfaces maybe, but okay. With struct definitions, you can create or define new data type in SIG. These instruction definitions work the same way as they work in C. You give a name to this new struct or to this new data type that you are creating. Then you list the data members of this new struct. Then you can also register functions, then become methods. In C++, when we create a new class, we normally have a constructor method, which is used to construct. In SIG, we normally declare the constructor and the destructor methods of our struct by declaring an init and a dinit method inside of the struct. This is just a naming convention that you will find across the entire SIG standard library. So in SIG, the init method of a struct is normally the constructor method of the class represented, while dinit is the method used for destroying the instance. Are both extensively used. User struct, blah 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 blah. Okay, so we have a user struct, ID, a string, another string, and you have your init function. So you just by convention. But this is nice, right? It means you can have more constructors without making a big fuss out of it. You return a user, print the name. No, very nice, very nice. And you have the self. No need to muck about with ownership, not yet. Blah 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 blah. User. Anonymous struct literals. Aha, so it is all of the squiggly brackets we have been using. They are actually these anonymous structures. Struct declarations must be constant. Types in SIG must be const or comtime. Okay, this comp time section is going to be kind of crazy, I guess. In the vec3 example below, this declaration is allowed because I'm using the const keyword to declare this new data type. The self argument. This self argument is a reference to the object itself from which the method is being called from. It is not mandatory to use the self argument, but why would you not use the self assignment? There's no reason not to use it because the only way to get access to the data stored inside of the data members of your struct is through this self argument. If you don't need to use the data in the data members of your struct inside your method, you likely don't need a method. You can just declare this logic as simple functions outside of your struct declaration. It's very verbose, this tutorial, but yes, the distance, yes, about the structure state. And I'm not going to read all of this. You learn by making mistakes. Type inference. C is a strongly typed language, but there are some situations where you don't have to explicitly write the type of every single object in your source code. Well, you know, now C++ also has the auto keyword. So, yes, auto keyword. Hey, can you infer the type of this value for me? The dot character. So I guess here I could do dot. No, I don't know, whatever. Another common place where we use type inference in SIG is at switch statements. I also gave some examples where we were inferring the data types. Okay, so yes. Comp time, inline, extern. So in function inline in, extern. This is from SIG world, very obvious. Comp time is a new concept. Order as an input. What did I do? Oh, copy link to highlight. Oh, I didn't know this existed. Anyways, the SIG compiler looks into the type of the input object, even to the switch statement. Atomic order infers the data members of typecasting. Typecasting, typecasting. We use typecasting. We want to change the data type. Most languages have formal way as well as we use as. In C we use typecasting syntax. In C we use ast. Yeah, you just cast it to a different type. Very nice, very nice. Thread pool. Oh, this is where it starts to get interesting. Memory allocators. How does SIG control memory? What common tools are used? Are there any important aspects to make memory different, special in SIG? Memory spaces. Every object that you create in your SIG source code needs to be stored somewhere in computer's memory. Depending on where and how you define your objects, you will use a different memory space or different type of memory store. Each type of memory normally serves different purposes. In SIG, there are 3 types of memories that we care about. They are global data register, the stack, and the heap. Compile time versus runtime known. One strategy that SIG uses to decide where we'll store each object that you declare is by looking at the value of this particular object, more specifically by investigating if this value is known at compile time or runtime. That's the stack versus the heap. When you write a program in SIG, the values of some of these objects that you write in your program are known at compile time. During the compilation process, the exact value of the particular object, knowing the length, blah blah blah. The compiler cares more about knowing the length or the size of the particular object than to know its actual value. But if the SIG compiler knows the value of the object, then it automatically knows the size of this object because it can simply calculate the size. Yes. In your source code, if the value of where was I? If the value of the object in question is known at compile time, then the SIG compiler. Okay. Yes. Let's look at the example. In the source code below, we have two constant objects, name and array declared. Because the values of these particular objects are written down, the source code itself, Pedro, and the number sequence 1 to 4. Yeah, the SIG compiler can. Okay, it's very verbose, this tutorial. The other side of the spectrum, objects or values are not known at compile time. Those goes into the heap because you cannot calculate their size, right? Function arguments are classic example of this, because the value of each function argument depends on the value that you assign to this particular argument when you call the function. For example, the function input length contains an argument named input, which is an array of constant UA integers. It's impossible to know the value of this particular argument at compile time. It is also impossible to know the size length of this particular argument because it's an array that does not have an yes, right? It will be an array of U8 integers, but we do not know at compile time its value and its size. This information is only known at runtime. Yes. The global data register. Blah, blah, blah. Any values is known at compile time. The dual between the stack and the heap. Stack, and then we go into detail explaining how stack works and how a heap works, which I'm not going to go into right now. We're going to quickly recap the learning summary, blah blah blah, stack overflows. And the heap is better performance, comes with many restrictions. One very interesting side note, if you don't know about this, NASA is only allowed to use the stack because you can run out of memory when you put things on the heap, right? So to make it deterministic, when they code, you get like the fixed size of memory, even if you are going to use it or not. Let's say you're expecting a string, you have to reserve the space on the stack, put your string in there, and that kind of allows you to do a static analysis, and you always know if you're going to run out of memory or not, which is vital for the space station, the space program. Okay, blah blah blah. After all of that, we finally arrive to allocators. One key aspect about SIG is there are no hidden memory allocators in SIG. What it means is that no allocations happen behind your back in the standard library. This is a known problem, especially in C++, because C++ there are some operators that do allocate memory behind the scene, and there is no way for you to know that until you actually read the source code of these operators and find the memory allocation calls. Many programmers find this behavior annoying and hard to keep track of. I've never had issues with this, but then again, I haven't done that much C++ programming. And also our modern phones have a lot of memory, so unless you're running like really old Android phones, you will not run out of memory most of the time. But in SIG, if a function, an operator, or anything from the standard library needs to allocate some memory during its execution, then this function operator needs to receive as input an allocator provided by the user to actually be able. This creates a clear distinction between between functions that do not from those that actually do allocate memory. Just look at the arguments of this function. If a function or operator has an allocator object as one of its input arguments, then you know for sure this function will allocate some memory during this execution. An example is the alloc print function from the SIG standard library. With this function, you can write a new string using format specifiers. So this function, for example, very similar to the function sprintf, I don't know what this does, in C. In order to write such a new string, the alloc print function needs to allocate some memory to store the output string. That's why the first argument of this function is an allocator object that you, the user programmer, gives an input to the function. In the example below, I'm using a general purpose allocator as my allocator object, but I could easily use any type of allocator object from the SIG standard library. So heap is just a heap allocator, I guess. I don't know what's the difference between these two. But okay, this is stasheet something, right? And then you just format in the string, and you need to pass your allocator. You get a lot of control over how much memory this function can allocate because it's you, the user programmer, that provides the allocator. This makes total control. Yeah, okay. So I guess if you are dealing with really sensitive applications where you cannot, like, you need to somehow validate, right, that your functions are not taking too much memory, or you have some sort of special memory, you can write your own allocator and just pass it down. What are allocators? Allocators in SIG are objects that you can use to allocate memory for your program. They're similar to memory allocation functions in C, like malloc and calloc. So if you need to use more memory than you initially have during the execution of the program, you can simply ask for memory by using the allocator object. SIG offers different type of allocators. They're usually available through the std heap module of the standard library. Thus, just import the SIG standard library, stop allocator interface. Okay, so there are interfaces. Alloc free, create, destroy. But the stack has a key limitation, blah blah, so no fixed length. In reality, there are two very common instances where this fixed length limitation in the stack is a deal breaker. The objects that you create inside your function might grow in size during the execution of the function. Yes, we saw that you can have undefined variables inside of your struct. So I guess you could allocate string, then set it to that. Yeah, so it grows. Sometimes it's impossible to know upfront how many inputs you will receive or how big this input will be. There is another instance where you might want to use an allocator, which is when you want to write a function that returns a pointer to a local object. Hey, I want to learn Linux. Where should I start? Jesus, I don't know, man. I didn't learn Linux. I just started using it. Which I guess is the best way to learn things, right? Like, just like me right now, I'm just kind of going through this tutorial, kind of flying through the tutorial, because you're not going to learn everything line by line, just by reading the thing once, right? Like, you need to write the thing. So I don't know. I guess, what do you mean by you want to learn Linux? Do you want to learn like the basic commands, Unix commands and pipes and all of this stuff, or I don't know, what do you want to learn from Linux? Like, it's a big operating system at the end of the day. There is another instance where you might want to use an allocator, which is when you want to write a function that returns a pointer to a local object. You cannot do that if this local object is stored in the stack, right? Because it gets deallocated. However, if this object is stored in the heap, then you can return a pointer to this object at the end of the function. Because you, the programmer, control the lifetime of any heap memory that you allocate. You decide when this memory gets destroyed and freed. That's what smart pointers are in C++. Yes, the command. I don't know, man. There are a bunch of Unix books, right? Like, you don't need a lot. It took 2 days to understand how to install the browser. I don't know. How did it take you 2 days to install a browser? Like, what type of Linux are you using? How did you land on my channel? Because I usually don't answer this type of questions. But I don't know, I started watching YouTube videos. I'm sure there are a lot of YouTube tutorials out there. These are common situations for which the stack is not good. That's why you need a different memory management strategy to store these objects inside of your function. You use a memory type that can grow together with your object. You can control the life. The heap fits the description. General purpose allocator, page allocator, fixed buffer allocator, thread save fixed buffer allocator, arena allocator, C allocator. Each allocator has its own perks and limitations. All allocators except fixed buffer and arena allocator are allocators that use the heap memory. Will be placed in the heap. Page allocator is an allocator that allocates full pages of memory in the heap. In other words, every time you allocate memory with a page allocator, a full page of memory in the heap is allocated. If you don't know how pages work, I don't quite understand it, but it's a way to allocate a chunk of memory, and you need to do reverse lookup, and then you can sequential. There's a very good what is this from Lori Wired Memory. This video is really good if you want to understand how memory allocation works. I would really recommend you guys to see this if this is something you're interested in. Okay. Most systems use a page size of 4 kilobytes. There's a amount of memory, then page allocator, buffer allocators, blah blah blah, arena allocators. Really interesting stuff. Why not? So first small project, I want to implement a base64 encoder decoder. Base64 encoding is a system which translates binary data to a text. A big chunk of the web uses base64 to deliver binary data to systems that can only read text data. This is something that each one of us uses. The most common example of a modern use case for base64 is email system. Blah blah blah. Let's learn about base64 because I always just use it and never understand it. The base64 encoding system is based on a scale that goes from 0 to 63. That makes sense. Each index in this scale is represented by a character. It's a scale of 64 characters. So in order to convert some binary data to base64 encoded, we need to convert each binary number to the corresponding character in this scale of 64 characters. Base64 scale starts with all ASCII uppercase letters A to Z, which represents the first 25 indices. After that we have all the ASCII lowercase letters, which represents the 26 to 51, and after that we have the 1-digit numbers to represent this, blah, blah. And finally the last two indexes in the scale, 62 and 63, are represented by the characters plus and forward dash. These 64 characters can compose the base64. That compose the base64 scale. The equal sign character is not part of the scale itself, but is a special character in the base64 encoding system. This character is only a suffix to add padding, right? Like we know this. So. creating the scale as a lookup table. The best way to represent the scale in code is to represent it as a lookup table. Lookup tables are a classic strategy in computer science to speed up calculations. The basic idea is to replace a runtime calculation, which can take a long time to be done, with a basic array indexing operation. Instead of calculating the results every time you need them, we calculate a table. So we can start building the SIG struct to store our base64 decoder encoder logic. We will start with the base64 struct below. For now, we only have a single data member in the struct, the member table, which represents our lookup table. We also have an init method to create a new instance of a base64 object and a char add method with get the character at index x type of function. So we just have a big array, 64 characters. Right, these are all of the possible characters we can encode, and then we just have a method that accesses the value of that character for getting the character on the lookup table. Okay. The encoder. This is the interesting part. The algorithm behind a base64 encoder usually works on a window of 3 bytes because each byte has 8 bits. So 3 bytes form a set of 8 times 3 equals 24 bits. This is desirable for the base64 algorithm because 24 bits is divided by 6, which forms 4 groups of 6 bits each. Therefore, the base64 algorithm works by converting 3 bytes at a time into 4 characters from the base64 scale. Aha. Okay, so you're just taking 24 bits and you can convert those into 4 characters, right, which we can encode based on this. Okay, easy enough, right? And therefore, the basic works by converting 3 bytes at a time, blah, blah, blah. It keeps iterating through the input string 3 bytes at a time and converting them into the base64 scale, producing 4 characters per iteration. It keeps iterating and producing these new characters until it hits the end of the input string, and you also need to take into account you might need padding, right? Like if you have 24 bits, if the last character you read in has 6 or less, then no, you don't think. What if you have a particular string that has a number of bytes that's not divisible by 3? What happens? If you would have a string that contains only 2 character bytes, such as hi, how would you the algorithm behave in such situation? You find the answer in figure, right? So age 72, I 101, these are 6, these are 6, these are 4, and then you fill the extra series to fill the gap. Complete blah 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 bits. That's extra zeros. That's y in figure. What when an entirely is empty or simply doesn't exist? So it says null. Okay. Padding group. Well, the algorithm is the same, right? So you turn those into the bytes, and then you take 6. No, then you take an entire byte at once. So here you have 1, 2, 3, 4 bit shifting and additions. Did they do bit shift and additions here? Okay. Bit transformation, DXI transformation, so DXI difference between encode and decode. If you don't have any previous experience with base64, you might understand it in encode and decode, blah blah. We want to encode, calculating the size of the output. One task that we need to do to calculate how much space we need to reserve for the output, both the encoder and decoder. This is simple math and can be done easily in SIG because every array has its length, numbers, elements, is the length property. For the encoder, the logic is the following. For each 3 bytes that we find in the input, 4 new bytes are created in the output. Yes. So we take the number of bytes in the input divided by 3, use this in the function, and then we multiply by 4. That way you get all you need plus the padding. Encapsulates this logic. So calculate the encoding length. It's less than 3, so it is the minimum size. And then you divide diff seal. I wonder what this does. For each byte in the input, 3 bytes will need to be produced. However, this time we need to take the equal character into account, which is always ignored by the decoder. In essence, we take the length of the input divided by 4. Yes. Then we apply a floor function on the result. Then we multiply the result by 3. And then we subtract from the result how many times the character equal is found in the input. Right, so if my base64 string has less than 4 characters, then the minimum size of bytes I can decode is 3. The floor I don't get, like every valid base64 string should have 4, but whatever. Groups times 3. Okay. Interesting. I think I'm going to stop it there for today. But yeah, SIG looks cool. It definitely feels, at least in these basic examples, like you can start writing SIG code fast, right? Like really fast. You don't need to fight any borrow checker. You don't need to know any, like a lot of special syntax. It has some syntax on its own, but no, it's pretty cool. I like it. Keep exploring it on another time. See you guys.